Okay, so now that we've looked at entropy at a molecular scale, we're going to do some calculations with it. We are going to calculate the entropy in two different ways. And just like the energy and entropy is a state function. So in order to kind of decide what a change in entropy is, it doesn't really matter how it changes. It just depends on how much you start with and how much you end with. So delta S is equal to S final, what we end with, minus S initial, what we start with. Entropy is a really hard thing to measure though. So we are going to calculate entropy in a couple of different ways. So for a process occurring at a constant temperature, and when we use the word isothermal means constant temperature. It doesn't change. The change in entropy is equal to the heat that would be transferred if the process were reversible divided by the temperature that it's occurring at. So we're looking at the change in entropy for kind of like our phase changes where we had the heat change, but the temperature stayed constant while something was melting or while something was vaporizing. We would be able to use this. So Q is the heat for a reversible process, and that is going to be in joules. And then for this one, our temperature does have to be in Kelvin because it's not a change in temperature, it's just a temperature. Okay, so our entropy change is the heat of the process divided by the temperature. So let's look at that. Elemental mercury is a silver liquid at room temperature. Its normal freezing point is negative 38.9 degrees Celsius, and its molar enthalpy of fusion is 2.29 kilojoules per mole. So remember this value, that enthalpy of fusion value, is associated with melting or freezing. That phase change there. Sorry. Okay, so what is the entropy change of the system when 50 grams of mercury freezes at the normal freezing point? Remember, Q is equal to H in a constant pressure volume system. Okay, so first off, I'm looking at this and I'm thinking, okay, mercury is freezing, which tells me that it is losing heat. Okay, so that means that it is going to be a negative Q value that I'm looking at. That freezing also tells me that I'm going from liquid at room temperature to solid after it's frozen, which is giving me kind of a guess that my entropy is probably going to be negative. I mean, it should be negative, okay, if this is what's happening. So we are going to look for our delta S, and in a phase change, we're going to use that Q value over the temperature. So we're going to use the Q value for our freezing, which is that fusion value. Now remember, this is kilojoules per mole. But what I see is that I only have 50 grams of mercury. So I'm going to need to cancel out that moles piece first. So I'm going to take my 2.29 kilojoules per mole, and I want my heat to just be in joules. So for every 1 mole of mercury, according to my periodic table, it's 200.59 grams. So moles cancel, and I'm in grams. And I have, let's see, I want to get kilojoules. So for every 1,000 joules, I have 1 kilojoule. So now I'm in joules per gram, and I have 50 grams. So that's going to get rid of that grams piece. And that leaves me with just joules. Okay, so when I calculate that, my Q value is going to be 570.82 joules. Remember we said, okay, it has to be negative because I'm freezing. So negative 570.82 0.82 joules. And then I'm going to divide it by my temperature. And so this is at the freezing point, or while it's freezing. And so it's going to be the negative 38.9. And I'm going to add 273.15. So, oops, I didn't get negative. 38.9 plus 273.15. And that's going to be 234.25 Kelvin. So when I take that, negative 570.82 divided by 234.25, I get a change in entropy of 2.44 joules per Kelvin. So what this is saying is that the entropy is increasing by 2.44 joules for every Kelvin, every single Kelvin that this goes up. Okay. Get another one. So the normal boiling point of bromine liquid is 58.8 degrees Celsius, and its molar enthalpy of vaporization is 29.6 kilojoules per mole. When bromine boils at its normal boiling point, does its entropy increase or decrease? Okay, so we have to think about what's happening to the bromine. So we're starting with liquid bromine, and boiling happens because a gas is forming. So it is becoming bromine gas. So we're going from a liquid to a gas, which tells me that entropy increases. So delta S is positive. Okay, so let's actually calculate. So we're going to calculate the value of delta S when 1 mole of Br2 is vaporized at 58.8 degrees Celsius. This 1 mole makes our job easier because we can just use the delta H VAP value as is. So the delta H is equal to the Q, and it is 29.6 kilojoules per mole, but we want 1 mole, so that I'm just going to get rid of that per mole. And I want it in joules. So I'm going to say for every 1 kilojoule, there's 1,000 joules. So delta S is equal to Q over T, where the Q is positive, or we're putting heat in to vaporize it, so the Q value is positive, 29,600 joules, all over our temperature, and our temperature has to be in Kelvin. So we're going to do 58.8 plus 273.15 to get 331.95 Kelvin. So my delta S is 89.2 joules per Kelvin. Okay, so you guys, we can use this delta S equation when we're at an isothermal process, meaning that the temperature doesn't change, and for our purposes, we know that happens during a phase change. So this is a great calculation to use for calculating the entropy change of when we change states of matter. It doesn't really work, though, for reactions, because most reactions are at least slightly exothermic or endothermic, meaning that their temperature does change. So the second law of thermodynamics states that the entropy of the universe increases for spontaneous processes, and the entropy of the universe does not change for a reversible process. So in other words, as a result of spontaneous processes, the entropy of the universe increases. So one of the ways that we're going to be able to decide if it's a spontaneous process is if we have an increase in entropy. So to do that, we're going to actually be able to calculate the entropy for a reaction. So we're going to be looking at these standard entropies. So just like our standard enthalpies, these are values that are given to us They are for a specific temperature. So these ones are 298 Kelvin room temperature, and a pressure of 1 atmosphere. Your gold sheet that you used for the enthalpies also has entropies on it. So you have a second column that has entropy. They tend to increase with increasing molar mass. Again, that's because of those microstates. And then entropies of elements are not 0. So with enthalpies, that was their natural state. They were 0. Entropy has to do with that movement and that randomness. And as long as we're not at absolute 0, everything has movement, which means that everything is going to have an entropy first. So let's look through our list. NH3 is 192 points. 191.5, 130 on our chart is joules per mole Kelvin. This per mole part we got rid of when we multiplied by the stoichiometric coefficients, so it's just joules per Kelvin value. Larger, more complex molecules have greater entropies. Why? It has to do with their movement. Their translational, their rotational movement is going to be greater. Remember, we've got each of these things kind of moving back and forth. So there's an opportunity for more movement, the more complex the molecules are. NH3. Okay, so let's look at this. We're going to calculate the change in standard entropy of the system delta S for the synthesis of ammonia from N2 and H2. So let's make a quick prediction if our delta S is going to be positive or negative. So I am going from 4 moles of gas, 2 different molecules, to 2 moles of gas. So I'm going to guess that delta S will be negative for this. It should be negative, okay? So let's go ahead and calculate this. So our delta S is going to be equal to the sum, of the products, so the entropy of the products, minus the sum of the entropy of the reactants. So this equation should look really familiar. It's the same way we just calculated the enthalpies. So we need to take into consideration our stoichiometric coefficient, so don't forget your balancing numbers. So we're going to start with our delta S is going to be equal to 2 of our NH3 minus, that's one thing, 1 of our N2s plus 3 of our H2s. Okay, so we need, 2 times 192.5 minus 1 times plus 3 times, okay, so let's do some math here. So 2 times 192.5 gives me 385 minus 130.6 is 391.8 plus the 191.5 to give us 583.3. So delta S is equal to 385 minus 583.3. That's negative 198.3. And then let's look at our units. So when we multiply these numbers here, those are the moles. So they'd be like taking 3 moles times 130.6 joules per mole K. The mole cancels and we're left with just the joules per K. So this is our final answer here. Oops. Guys, pause your video. I want you to try this one next. Okay, so hopefully you got the calculation. One thing I want to point out is that in this scenario, water is a gas, so you should have used the value 188.7 versus the value for liquid water. So if you didn't get the same answer as me, check that first. So I got 180 joules per Kelvin. So I got a positive entropy value. So let's double check that that makes sense with our reaction. So I'm starting with 1 mole of solid and 3 moles of gas. And I'm ending with 2 moles of solid and 3 moles of gas. So I'm increasing the total moles. I'm going from 4 moles on this side to 5 moles on that side. I've still got 2 things. So that makes sense to me that I would see an increase at an isothermal situation, so where my temperature is the same. Okay, so a couple other things, you guys, about entropy. Heat that flows into or out of the system changes the entropy of the surroundings. So if there is a temperature change, that heat had to have gone somewhere, just like we've talked about in the first law of thermodynamics, is that we can't lose or gain that energy or that heat from nowhere. So for an isothermal process, meaning the temperature stays the same, the change in entropy of the surroundings is equal to the negative Q of the system over T. So if the system gains heat, it had to have come from somewhere. It was lost by the surroundings. So we can calculate the entropy change of the surroundings as well. The universe is the system and the surroundings both together, and so if we're looking at a change in entropy of the universe, we have to take into consideration the system and the surroundings, so we would add both those entropy changes together. And for a spontaneous process, the change in entropy of the universe is going to be greater than 0. Okay, so a spontaneous process is going to increase the entropy or the randomness of the universe. Okay, so what we can do then is kind of derive an equation that compares the entropy of the surroundings with the heat in the system, and we can look at combining those two. And we're going to use this to decide if a situation is spontaneous or not, taking into consideration the temperature, the entropy, and also we'll have to take into consideration this enthalpy piece, this heat of the system. Okay, next time.